Okay, so we're on to the next video now. You'll probably see already. I'm doing it right now, but I'm assuming this will be much shorter than the one I did for the first part. But this is just getting us ready to do our applications of vectors, which I will be going over with you guys during our block periods. So we have to understand how to write vectors in trig form. So here's the setup for you. So if you have the vector AB, but this one I'm going to add an angle to represent, because this is, with just component vectors, there's no angles involved. But as soon as you add trig, now you're really able to calculate, like literally calculate the direction. And I said there are two big components of vectors, and that's direction and magnitude. And just regular component form is really great for finding that magnitude, but it's really not good for finding direction. So that's where this trig form comes in. You're able to actually now do that. So if you have a vector written in the form AB, and let me change that color there. So your A value, if I write my vector, here's my vector. Now in this case I'm going to actually put my angle in there too. So I have another component to add, but this is your A value. Your A value is the magnitude of the vector times the cosine of theta. Now again, understand normally what you would do is you just call it cosine theta if the magnitude is 1, if it's a unit vector. But as we said, when we multiply by a scalar, every value inside that vector gets multiplied by that same scalar. So like, remember if I was multiplying c by the vector AB, we just distribute. That's all I'm doing. So that's what I'm doing here. I'm multiplying by a scalar for both my horizontal and my vertical components. So obviously this represents my B value. So I can write a vector in component form in terms of sine and cosine. And what I do when I write it in terms of sine and cosine, I've included now that angle. Okay, so if you have your vector A, B in component form or in terms of I and J, you can now write out your vectors in the following forms. You can call it magnitude V, cosine theta, and magnitude V, sine theta. So you can write it that way, or you can write it as the magnitude V sine theta times I plus magnitude V cosine theta times J. And again, I tend to use this one a lot, but again, it just depends on the scenario. As you get into harder material that you may need, to write in terms of I and J with your trig functions as well. But you'll see me do this one quite a bit because we don't get to anything too complicated with our trig forms. But anyway, we need to know how to work with this. And that's really our main goal today. Just make sure you know how to work with that. And if you do, you'll be okay. So, and then we can, do our applications and whatnot. So first example I have is just working with this and getting used to it. So here I want you to find the horizontal and vertical components of the following vectors. And again, all I'm going to do is give you the magnitude and the direction. And we're going to write this in terms of I and J, but again, I can write it in both forms, honestly, so I'll do that just so you can see it. So with the first one, we are given a magnitude and we're given a direction. So the big thing when I write this out is the direction. That's going to tell me how to draw my XY plane. It looks like I am in the third quadrant, so I'm going to draw the third quadrant of my XY plane. So when I draw my vector, I'm going to put it here in component form, so that means I'm starting at 0, 0. And 210 is 30 degrees past 180. So I kind of know where to put it, which is good. And I know this length is 55. So this is where it's really nice if you know one of two things. If you know either unit circle or you can use your special right triangles, it doesn't matter. Now I've been with you guys a component of using the unit circle all along, but as sometimes you'll see the special right triangles are also useful. Here it really doesn't make much of a difference. It's about the same amount of work either way, but I'm going to focus on unit circle. Just know if you know your special right triangles, that will also work for you. So here's what I'm looking at. I know this angle right here is 30 degrees, so if you're going to use your special right triangles, you'd focus on that angle. I also know this angle right here is 210 degrees. Since I'm using the unit circle, I'm going to focus on that. But remember, even when I do that, I still kind of think of the right triangle. So regardless, just so you know, this is magnitude V cosine theta, and your vertical component is magnitude V sine theta. So my A value is going to be the magnitude of V, which is 55, times the cosine of 210 degrees. That's going to be my horizontal component. I plugged in theta, which is 210 degrees, and I plugged in my magnitude, which is given to me. So if I know cosine and I'm going left a lot, I know it's going to be negative radical 3 over 2. So you plug that in. And 55 and 2, well, those don't cancel. So my A value is negative 55 radical 3 over 2. So that is my A value. Next up, my B value. So B is going to equal 55 times the sine of 210 degrees. So that's going to be 55, and the sine of 210 degrees, I'm going down a little, so that's negative 1/2. And with this one, it's the same thing, 55 and 2 don't cancel, so I get negative 55 halves. So if I wrote my answer out, my vector V in component form is going to be negative 55 radical 3 over 2, and then negative 55 halves. You can also write it as negative 55 radical 3 over 2i. Just kind of looks bad, but that's what it is, minus 55 halves j. So both of these are good. I mean, it did say right in terms of I and j, so I guess the second one is more correct based on the directions, but they're both fine. Okay, so that's going to be example A, just using your trig form of vectors. Same thing here on example 2. This one, or example B, this is 120 degrees, so I know I'm going to be in the second quadrant. So as I write this out, I'm in the second quadrant. I'm going to draw my vector right up here. I know 120 degrees is 30 degrees past 90, so that's kind of useful. You can set up your triangle however you want. But again, I'm using this angle right here, 120 degrees. I know my magnitude is 3, and I'm ready to go. So remember your horizontal component. Actually, I'll draw my triangle the other way. It's probably better, although it doesn't really matter. I didn't mean to do all that, though. Okay, that's fine. I can fix that. Okay, so if I'm drawing my right triangle, remember I'm going left. In this case, my A value, so that's my A, and that's my B. So here we go. A is going to be my magnitude V cos theta. So it's going to be 3 times the cosine of 120. Don't worry about the negative A, because the cosine takes care of that. So when you're calculating this, this is 3, and the cosine of 120, that's left a little. So it's going to be negative 1/2. So I'm left with negative 3/2 for A. For B, that is the magnitude of V, so 3 sine theta, so sine 120. So if I'm doing this, that's 3, and then I'm going up a lot, so that's positive radical 3 over 2. So I get 3 radical 3 over 2. So if I'm writing this in the proper form here, it's AI plus BJ. It's going to be my vector is negative 3/2 I plus 3 radical 3 over 2j. And there you go. There's vector V. So that's getting you used to finding your horizontal and vertical components, which we're going to need to do when we do our applications. All this stuff is building up to the application component here. No pun intended with the component. And the last thing we're going to do is finding magnitude and direction. And that's, again, those two important parts of a vector are magnitude and direction. So if I'm giving you a vector in component form, and I got to find both those things, well, we're going to need to do a little bit of trig to find that second piece. Magnitude, we should already know how to do that from our previous lesson. So anyway, for this guy, it looks like I'm in the third quadrant. So when I write this out, I got a ton of space here, so I'm going to try to make it a little big. But this one, I'm going to go left 1/2 and down radical 3/2. And just as I did all the other ones, though, especially since I'm doing direction, drawing a right triangle is going to be crucial here. So I'm going to draw a right triangle, and I'm going left 1/2 and down radical 3/2. So first off, let's get the magnitude of this vector. So the magnitude in this case is going to be the square root of a squared plus b squared. So it's -1/2 squared. Although you should already know the answer to this one, but if you don't, you'll see it in a second. And then b squared is negative radical 3/2 squared. So here we go. So 1/2 squared is going to be 1/4. Radical 3/2 squared is going to be, in this case, plus, because it's plus a negative. You're squaring the negative, so it's going to be plus anyway. So that's going to be 3/4. So this becomes 4/4 when you combine them, which is 1. The reason for that, when I said I already knew the answer, is those points are on the unit circle. So that means the radius, which is this length right here, is 1. So that's really good. Now, the other thing that's really nice about this is the direction. I already know the direction of this because it's on the unit circle. So if you think the point on the unit circle, and again, this doesn't necessarily have to be to scale, if you're going left a little, down a lot, and again, I'm just pulling this straight from the unit circle, that is 30 degrees before 270, which is 240 degrees. So I have my magnitude and my direction. So those are those two components. Now, you don't always get values that are on the unit circle. That's what this one had.